So, our next lesson today is going to be types of reactions. So lesson number 2. We just finished a lesson on how to balance chemical reactions. We're going to build on that with now, what if you're just given reactants? How would you figure out what the products will be? Now, the big idea is there are many types of reactions that can be identified by the species involved in the reactants. So, our first thing we're going to talk about is what are chemical reactions? Well, there are 6 major classes of chemical reactions we're going to talk about. So there's 6 major classes of chemical reactions that we're going to study, okay? And what a reaction is basically where the reactants are different from a product. A reaction occurs when the reactants are different from the products. Okay, now a reaction is typically written like this. So when we did balancing, you usually see a reactant will somehow progress onto products. Okay. Now the arrow that is written here only shows the direction the reaction takes place. It doesn't tell you how long it takes this reaction. So it could be a quick millisecond reaction, or it could be ones that last for years. So the arrow doesn't really tell you time, it just tells you direction. Now again, why do we want a closed system, or in this case an isolated system? Again, we want to make sure we can do our calculations. Our calculations are important because if it's not, in this case, a closed or isolated system, we will have things entering and leaving, and thus it will change our calculations. But the thing about closed systems, in this case isolated systems, is usually they allow us to set specific properties to our reaction. So that's one of the big key driving factors of why we want a closed system. So that's what we got to discuss to start off with. Now we're going to move on to the 6 different types of reaction. You've learned a few of these, or actually most of these, in Science 10, so it should be quite a quick review. Now, our first type of reaction we're going to is what we call a synthesis reaction. A synthesis reaction is, just like the word it states, synthesis means to make. So that's what the word synthesis means. So what does that mean, to make? Well, a synthesis reaction occurs when 2 or more reactants form one product. So what does that look like? Well, it looks like this. You have 2 reactants or more, A plus B, will form together to form AB. They're going to join together. An example of something like that would be, for example, when hydrogen gas, plus oxygen gas will join together to form water. So that's an example of a situation like that occurring. Now, how can you figure out what your products will be, or what can you figure out if this is a synthesis reaction? A lot of times the reactants, are usually elements. Okay, and the product is usually formed by these elements. Now, if it's an ionic product, such as, for example, A is a metal, B is a nonmetal, you still have to make sure your charges are balanced. And what this means is if you have aluminum plus chlorine, okay, now if chlorine is reacting with aluminum, well, aluminum has a +3 charge, chlorine has a -1 charge, you're going to need 3 chlorines to form this, and thus it becomes AlCl3. The second type of reaction we're going to talk about is the decomposition reaction. So it's the opposite of a synthesis reaction. Okay, so it's the opposite of synthesis. Now, decomposition reaction is where usually one product breaks into 2 or more, not one product, one reactant breaks into 2 or more products. Now in reactions like this, what it looks like is A, B will again break into A plus B. So we gotta make sure that we know what these chemicals will be. Now usually this would be a compound breaks into its element, but not always the case. It won't. Sometimes it might break a compound into another compound, but most of the time it is usually a compound breaking apart into its elements. So an example that would be, for example, if you talk about NaCl will break apart into Na plus Cl2. So this is aqueous, this is solid, and this is a gas. Now, the next type of reaction we're going to talk about is going to be our single replacement reaction. A single replacement reaction is one where you're going to usually have one element reacting with a compound. And what's going to happen is that the element is going to kick off the same type of element in that compound and replace it. That's why it's called single replacement. So if the element equals a metal, it will replace metal and compound. And if it's a non-metal, it will replace the non-metal in the compound. So, what does this look like? Well, it can happen in 2 different cases. For example, if A reacts with BC, right? A is your element, BC is your compound. And let's say, for example, A is a metal. If A is a metal, then it's going to switch out with B. So what's going to happen is you're going to get B getting kicked off while A takes over its place. So you're going to get B by itself and AC like so. So that's one scenario that's happening. What happens if A is a nonmetal? Well, if A is a nonmetal, then in this case, you're going to get A kicking out C while C comes out, and you're going to get C plus Ba. So either of these cases could occur. An example of one of these cases could be, for example, let's say, for example, you have iron plus copper 2 chloride. When this reacts, well, as you can see, iron is a metal. It's going to replace with the copper and kick the copper out. And in this case, what's going to happen is you're going to get copper by itself an iron reacting with your chlorine. So that's an example of this happening. Now, why does this occur? The reason why this occurs is usually because the iron is much more reactive and it wants to remove the less reactive copper in this case. So a more reactive element usually kicks off a less reactive element. Alright. Now here's the big thing though. You gotta make sure the charge is still balanced. So make sure ionic charge is still balanced. Like we did when we did our previous example of synthesis. Now the next example is called a double replacement. A double replacement is a reaction that occurs it's a reaction between two ionic compounds. Okay, and it's basically the non-metals will switch partners. That's really what's going to happen. Now, why does this happen? Well, what you're going to learn in Chemistry 12 is that you will find out that this happens because you're trying to create a stable precipitate. But that's more of a Chemistry 12 topic. Now, an example of this, what's going to happen is you have AB is going to react with CD, and when this happens, well, A is going to swap with C. Or you can also think of it as B will swap with D. And when this happens, you're going to form a new compound. You're going to have, in this case, AD plus CB. So an example of this happening is, for example, if you have, for example, NaCl plus, let's say, for example, H2SO4, when these react, you're going to have a double replacement. So you have Na react and swap with H, the hydrogen here, and then that means the chlorine, and in this case the sulfate, can also switch, and you're going to get these chemicals. The Na, which was initially with chlorine, is now going to be with sulfate. So you're going to have NaSO4. But this is not correct, because what we should know is that sodium has a +1 charge, but sulfate has a -2 charge. So in order for that to balance, you need 2 sodiums. The next thing you're going to have hydrogen, which was initially with the sulfate, will now be with the chlorine. And this will be HCl. And this is going to be balanced with charge because hydrogen has a +1 charge, chlorine has a -1 charge. So these two, in a sense, they swap partners. So that's what we call a double replacement. Now, a double replacement can have a special type, which we call an acid-base neutralization reaction. So this is a type of double replacement. So I'll write DR as double replacement. So what this means is you're going to have an acid reacts with a base to form a salt and water. Now, you might remember that acids are any chemicals that have hydrogens in usually the start of their name, and bases are usually chemicals that have OH at the end of their name. So what does this look like? Well, you could have, for example, some acid, hydrogen plus some nonmetal, plus some base, metal of the base, plus OH, is going to react to form a base, to form a salt and water. Now what the salt is going to be made up of is usually between these two things. The nonmetal, oops, that's too hard to see, a nonmetal of the acid and the metal of the base. So that's why you're going to have B and A. And the other thing is you're going to get, because it's a double replacement, because these two swapped, you're going to have HOH, which is your water. So that's a type of acid-base neutralization that you can have. So, what does this look like for an actual reaction? Well, let's say, for example, you have hydrochloric acid. So here's our example. And you're reacting with, for example, NaOH, so sodium hydroxide. When these two react together, you're going to get hydrogen and the sodium, in a sense, swap places. And thus, because of this, you're going to form this product. You're going to form NaCl. As you see, Na came from the metal of the base, and Cl came from the non-metal of the acid. And your other product is going to be water. It's going to be HOH, or you can write it as H2O, or you write HOH, based on when you're balancing or not. Now, what you can do, because this is a video, is that a titration is a way of finding the concentration of either your acid or your base. What I want you to do is you can go on YouTube and look for a video of a titration. It's not the most exciting thing, but it's a very useful chemical tool. The last type of reaction we're going to talk about is called a combustion reaction. It's usually the one that students have the most fun in, because it's what you usually say is an explosion. But it's usually just anything that produces energy in the form of a fire, or in this case, yes, an explosion. So what it is, it's a reaction between a hydrocarbon and oxygen gas. Okay, so hydrocarbon, remember hydrocarbons are anything that contains hydrogen and carbon, and with carbon as backbone, and O2. Okay, so if you want to write a little note, hydrocarbon is an organic compound with carbon as a backbone. So, what you're always going to get when you react a hydrocarbon and oxygen gas is you will always form Cl2 plus H2O. Always, always, always. It doesn't matter what the hydrocarbon is. It could be 100 carbons and 200 hydrogens. It will always form CO2 and H2O. But here's where it gets a bit tricky. If hydrocarbon contains sulfur, so for example gasoline, then you're also going to form one additional product. And the additional product is going to be SO2, sulfur dioxide. I'll show you an example what that looks like. Alright, so sulfur oxide, we're going to talk a bit more about this. Now, here's some examples of this. So an example of this would be, for example, if you have some hydrocarbons, CXHY, so X and Y are just numbers, plus O2 will always gives you CO2 plus H2O. So an example of that would be, for example, let's say for example C5H12 plus O2 will always be Cl2 plus H2O. But if your hydrocarbon contains sulfur, so for example, if I write C5H12S, so that's sulfur right there. If that's the case, you're going to now form an additional product. So you have Cl2 plus H2O, but the last product is going to be SO2. So make sure you remember this last product there. It's very important that we know this. So what's so special about SO2? Well, because as I stated, SO2 is in a lot of your gasoline and produced from your cars due to gasoline. SO2 is actually one of the reasons why we get acid rain. So when this reacts with water, it actually forms sulfurous acid, which is H2SO3, which is your acid rain. Now, what you could do if you're still a bit confused is you could turn to your Hebden. So this is from your Hebden, and you could turn to page 118, and there will be a table there available to you going over all these types of reactions. Now, Usually I would do a demo of a milk carton rocket. Now because I can't really do this demo in my house, what I'm going to do is I'm going to show you a video of this demo being done a few years ago in one of my classes. So this is what happened. So you have a milk carton here. You have a meter stick attached to a wooden splint that's currently on fire. Inside this milk carton is pure methanol that has been vaporized. And when you bring this lit flame fire right there from the wooden splint, you're going to now cause a combustion reaction to occur in this milk carton. And this is what's going to happen. So it's a bit fast. I'll show it again. And as you see, if I go to about here, maybe, if I could try, let's see if I can pause the video at the right time, you could see that it fires pretty violently. And that's why this demo, it must be done at a safe environment. You must be safe at all times. You might even notice that most of the students are pretty far away and they're wearing goggles, and you have to create a barricade along with the desk. But just make sure, again, this is why this must be done under adult supervision and done in a safe environment. So now let's practice what we did today on types of reaction. So you're going to be given questions like this. And sometimes the question can ask you to predict what type of reaction is it. Complete the reaction, what will the products be? And then balance the following reactions as well. So let's take a look at the first one. The first example you see is aluminum plus oxygen gas. Now, when you see aluminum and oxygen gas, these are two elements. And because they're two elements, they're going to react to form usually a product. So in this case, this is a synthesis reaction. So what's going to happen? Well, I'm going to do a little intermediate step that you don't have to do. Because aluminum is a metal and oxygen is a non-metal, they're going to form ionic compounds. I just want to see how I could balance these charges out. So if we look at it in our periodic table, aluminum has a +3 charge. And oxygen, when this oxygen reacts, it's got to turn to ion, and it's going to be O, and it's going to have a -2 charge. Now you're going to try to find a way to balance these. In this case, you're going to need 2 aluminums and 3 oxygens to balance them, and thus you're going to form a single product, which is going to be Al2O3. So that is what your first example is going to be. Now you're going to need to balance them now. So what do? Well, you see that you have 1 aluminum here and 2 aluminum on your product side, so you're going to need 2 aluminum like so. Now you have 2 oxygens here and you have 3 oxygens here. We've come across the example of a double odd even rule. Now if you don't know what the double odd even rule is, I would advise you to go back to the balancing chemical equations video and you'll actually see how the rule is applied. But what this means is when you have an odd number on one side, in this case a product side, and an even number of the same element on the reactant side, and you don't want to use a fraction method, we call it, then you can just double everything you've balanced. So in this case, this 2 becomes a 4. And what this would have been a 1 initially, because you would have put a 1 here to balance the aluminum. This 1 now becomes a 2. And now what happened is you turn that odd number into an even, because 2 times 3 is now 6. You now have 6 oxygens here. In order to balance it here, you're going to need to put a 3. And now this is now balanced. Our last step is to put states. Now what you got to remember is, most of it is common sense. Aluminum is a metal. Because it's aluminum metal, you see this quite often in tinfoil, it's a solid. Oxygen is a gas, so it's oxygen gas, it's a G. Al2O3, you could put this as aqueous if you want. Now some people would say that no, that's not aqueous, that is aluminum oxide, that must be rust, that's solid. In this class, because we're not figuring out the solubility of a element of a compound yet, that's a chemistry 12 topic. For now you can write this as aqueous to go with, okay? Let's try the next example. So again, if you want, you could pause this video at any time. That way you can try these examples out first before you move on. So NO2, you just see one single reactant. Nothing else. In this case, you should right away notice that this must be a decomposition. What this means is that this compound is going to break apart into its elements. It's made up of nitrogen and it's made up of oxygen. Well, what this is going to break up into is that nitrogen is going to be one of the products. It's going to be N2. And oxygen is going to be the other product. Now, you're going, why is it N2 and O2? Now, if you have never learned this before, this is called a diatomic molecules. I'm going to write this on this side really quickly. The diatomic elements. So let me fix this really quickly. The diatomic elements. These are elements that can only exist in pairs in nature. They cannot be found alone. And these are usually what we call hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and the last one is chlorine. Now, how can I remember all of these? Well, one of the easiest way you can remember them is an acronym that has been used quite often. It's called Hofbrinkel. H-O-F-B-R capital I-N-C-L. That's one way you can remember Hofbrinkel. Now, the other way I sometimes could teach it is a 7 plus H. Now, you're going, what is a 7 plus H? Now, if you open up your periodic table, you would see that every one of these elements starting at nitrogen and going all the way down to iodine forms the number 7. So it goes like this down the periodic table, where you're going to have nitrogen here, oxygen, fluorine, chlorine, bromine, and iodine. And that forms a 7. And then the other thing is you're going to have hydrogen by itself, and that's why I call it 7 plus H. So these are called diatomic molecules. They exist in pairs if they're by themselves. So you can't write them as just hydrogen by itself. It must be H2. So hopefully this makes sense. So in this case, this is why it's N2 and O2. So now it's balanced. You see that you have one nitrogen here, you have 2 here, so you need to put a 2 in front of this NO2. And you see that you have 2 O2s, which means that you have 4 oxygens. So you need to put another 2 right here to balance them out. The last step is to write their states. Now, NO2, you might not know what the state of this is. Most of them, again, is common sense, but sometimes you never come across these compounds. So nitrogen dioxide is actually a gas. Nitrogen itself is a gas because the majority of our atmosphere is nitrogen, and then oxygen is a gas. So let's move on to the last 3 examples. So the last 3 examples here is the first one is you have chlorine, just an element, reacting with a compound. So what does that mean? Well, element reacting with a compound, this is a single replacement. Okay. Now, single replacement, I'll write it as SR. That way it's a lot short form. Just like double replacement is DR. In this case, because chlorine is a non-metal, it will swap and kick out the non-metal of the compound, which is bromine. So when that happens, bromine gets kicked out by itself. What do we know about bromine though? It's diatomic. And because it's diatomic, it's going to be Br2. The other element, the other compound is going to thus be Ca and Cl. But we gotta make sure, because this is ionic, we gotta make sure its charges are balanced. So if you look at your periodic table, calcium has a +2 charge. Chlorine has a -1 charge. So if you write this out, Ca is a +2, chlorine is a -1. You're gonna need 2 chlorines to balance out the 1 calcium. So in this case, it's CaCl2. Our last step is to balance, but if you look at this, this is already balanced because you have 2 chlorines here and 2 chlorines here. You have 2 bromines here and 2 bromines here. You have 1 calcium, 1 calcium. So we gotta put the states down. Chlorine is a gas. Because it's an ionic compound, you could put it as aqueous. Bromine. Bromine's a weird one. Bromine is actually a liquid. It's one of the only elements that's a liquid in room temperature. And calcium chloride is aqueous. Our next reaction is going to be a bit interesting. As you can see, we have hydrogen acting as a metal, and we have OH, hydroxide, acting as a nonmetal. This is an acid-base neutralization, so you can write this as a neutralization reaction. So it's a type of double replacement. Because the type of double replacement, what's going to happen is the hydrogen is going to swap with the strontium. And when this occurs, you're going to have hydrogen with the OH, which is what water is going to be, and you have strontium with the NO3, and that's your salt. So you have strontium with the NO3, but you gotta make sure, again, ionic compound, they must balance. The strontium's charge is +2, NO3 nitrate is -1, so you're going to need 2 nitrates to balance out the charge. In order to write that, you gotta put a bracket around NO3 with a 2, and that's because it's polyatomic. The other compound is going to be water, which is, you could write as HOH for now. So now we got to balance now. So as you see, you could start with balancing out the metals. So when you balance out this metal, strontium, you see you have 1 strontium here, you have 1 strontium here, that's balance. But what's attached to strontium? Hydroxide, OH. You have 2 OHs here, you only have 1, so you must put a 2 in front of this. Okay, what's next? Well, this hydrogen over here on the reactant side only has 1, but you have now 2 hydrogens here, so you must put a 2 in front of the HNO3. The last step, look at what the NO3 is. You have 2 NO3s on the reactant side, and thus you have 2 NO3s on the product side. This is now balanced. So let's put the states down. HNO3, you can write this as aqueous. SrOH2, you can write this as aqueous. SrNO32, you can write this as aqueous. And last but not least, HOH, which is water, that's a liquid. So, if you could pause the video at any time, we could work on the last example, and then this lesson is going to be done. Now, the last example here is C4H8S plus O2. This is, right away you could notice, hydrocarbon and oxygen. That must form a combustion reaction. And now, a combustion reaction is one in which you always form these 2 products no matter what. CO2 plus H2O. Now, the reason why I'm writing H2O as H2O, not HOH, is because this is a non-metal or a covalent reaction. These involve ionics. That's why I usually want to write HOH that way, because if it's ionic, it's easier to balance. But in this case, you don't need to. But what do you notice about this hydrocarbon? It contains sulfur. And when it contains sulfur, you can add 1 additional product, which is SO2. So let's try balancing. So in this case, our first thing to balance, let's balance the carbon. We have 4 carbons here. We have 1 here. So we should put a 4 in front of this CO2. You have 8 hydrogens here. You have 2 hydrogens here. So you should put a 4 in front of this hydrogen. Or this water, I mean. The last thing is, if you look at sulfur here, so there's 1 sulfur here, there's 1 sulfur here, that's balanced now. So let's now balance the oxygen. You have, right now, a total of 4 times 2 oxygens here, 8 oxygens. 4 times 1 oxygen here, that's 4 oxygens, and 2 more here. So you have a grand total of 14 oxygens. What should you put in front of this to become 14? Well, 2 times 7 gives you 14, and that will help balance your reaction. Now, what should you do to write the states? Well, because this is not aqueous, it's not ionic compound, it's kind of difficult because you don't know if it's going to be a solid, liquid, or gas. It's okay if you put either. I will put this as a liquid. But oxygen gas must be a gas. Just like carbon dioxide must be a gas, water must be a liquid, and sulfur dioxide is actually a gas. So this is the lesson on the types of reaction. Now what I'm going to ask is that you do your homework on page 118, numbers 65 to 67, ACE. Now what does ACE mean? ACE just means you do every other letter. Now I'm going to take a look at your textbook really quickly to make sure that this is not a lot of questions, so I'll be right back in about 2 seconds. So if I flip to page 118, I could see that you have approximately, so if you do 65 to 67, it's not too many questions because, as you see, some of them are balancing and some of them are predicting, so it's a good practice to make sure you get good at predicting types of reactions. As always, if you have any questions, send me an email, and remember to stay safe and healthy. I'll see you soon.